Hello, everybody. I'm Artur Mozers, and I represent the Laser Center of University of Latvia. And I'm grateful for the organizers to providing me this opportunity to present our research in a talk about the high-order atomic coherences for the elimination of nonlinear Zeeman splitting error. So this research project is in its early stages. That's why the results are yet to be obtained. But regardless, I will try to give the general idea behind this research project. So a brief introduction. So optically pumped magnetometers possess very high sensitivities for the magnetic field measurements that are comparable to the sensitivities obtained by the squid magnetometers, but offer some advantages. And the best sensitivities of atomic magnetometers can be achieved at the zero magnetic field. However, some applications require to measure small changes in the ambient magnetic field. For example, the Earth's magnetic field, which is on the order of 50 microtesla. And here are some examples of these applications. So geological exploration, detection of explosive devices or submarines, measurement of biological magnetic fields, and mapping and subsequently navigating by the Earth's magnetic field. So what happens if you take a scalar atomic magnetometer and expose it to an ambient magnetic field? So actually the accuracy of the magnetic field measurement degrades, and this leads to heading errors. So that means that the magnetic sensor and its relative orientation to the magnetic field that you're trying to measure will impact the accuracy of your measurement. So some sources of these heading errors is the nonlinear Zeeman effect caused by the coupling between electron spin and the nuclear spin, light shift caused by the dependence of the interaction strengths between magnetic sublevels on the relative angle between the beam and the magnetic field, and also the nuclear Zeeman effect caused by the different gyromagnetic ratios of the two ground hyperfine states. The major cause of the heading error is the nonlinear Zeeman effect. So there have been several means of mitigating the nonlinear Zeeman effect error. And the first approach tries to compensate the error by using various theoretical or physical techniques. For example, by using counterpropagating circularly polarized, oppositely circularized light beams. Another approach is by addressing atomic states for which the nonlinear Zeeman effect is reduced, for example, by spin locking an additional radio frequency to the atomic ensemble. And a third approach, which may be actually the most obvious one, is to use magnetic sublevels, the energy and the energies of which are linearly dependent on the external magnetic field. For example, the -2 and +2 magnetic sublevels of the 87th rubidium F equals 2 hyperfine ground state. So how can we make use of these linear dependent magnetic sublevels? So light carries an angular momentum equal to 1, and that means that the highest order coherence that can be created is on the order of 2. But these magnetic sublevels are further apart from each other. So we will have to have, so 2 second order coherences are necessary to create these delta coherences between these magnetic sublevels. So this is a multi-photon process. And that means that while the first coherence between the -2 and the 0 is created, the second one between the 0 and the +2 has not yet decayed. So what happens? So actually, when you let me jump back one slide. And so actually, when you perform this, you create not only this delta m equals to 4 coherences, but you also create the delta m equals to 2 coherences, and also delta m equals to 1 coherences. So when you create it like this. So what happens if you subject it to an external magnetic field? Well, the angular momentum distribution starts to precess about the external magnetic field axis, and these coherences are destroyed if you're using a continuous excitation. But if you're using an amplitude modulated excitation, and the frequency of this amplitude modulation coincides with the precession frequency, then these coherences can be restored. And up until this point, the delta m equals to 4 signal has been accompanied by a strong delta m equals to 2 background. So somehow we have to get rid of this delta m equals to 2 coherences background. So we propose a protocol like this. So first you modulate to create these coherences in the external magnetic field. And then at what point you flip the phase of this modulation by 180 degrees. And this means that now the modulation will be out of phase for the delta m equals to 2 coherences, and they will be actively destroyed, while it will be still in phase with the delta m equals to 4 coherences. And after a brief wait time, only the delta m equals to 4 coherences remain, and that is how you obtain the delta m equals to 4 coherences. Yes. So how we intend to observe these delta m equals to 4 coherences? So after this brief wait time, we intend to observe the fluorescence signal along the magnetic field axis for different amplitude modulation frequencies. And when the amplitude modulation frequency coincides with the 2 times the Larmor frequency, so the alignment in the ground state is created, and that means that the absorption is diminished, and also that means that the fluorescence will diminish at that point. But if the modulation frequency does not coincide with 2 times the Larmor frequency, then the alignment in the ground state is not created effectively, and this will increase the absorption and therefore increase also the fluorescence. So this is the signal that we expect to observe. And this is the proposed experimental setup. So we intend to use a high-power laser, and then the output of the laser will be modulated by an electro-optical modulator. And then the beam will enter a rubidium cell, and we intend to use 2 types of cell just to see how it impacts the results. We intend to use a cell with the natural abundance of both isotopes, and another one which is isotopically pure. And the magnetic field will be applied by Helmholtz coils in this direction, and also the fluorescence will be collected in this direction. So that's a brief overview of the experimental setup. And as I have no real results to present, here's a brief summary. So the goal of this project is to demonstrate the feasibility of increasing the accuracy of atomic magnetometer that is immune to the nonlinear Zeeman splitting error by excitation of high-order atomic coherences. The proposed method will provide a signal that is linearly dependent on the external magnetic field. We also intend to obtain experimental results by implementing the proposed algorithm for the creation and detection of the delta m equals to 4 coherences. And we also intend to develop a thorough theoretical description for modeling these signals, which involve these time-dependent physical processes, and analyze experimental results. And just a small advertisement, currently in Latvia, there are some postdoc grants available. So if you're interested in doing your postdoc research in Latvia, you can follow this link, or you can try to contact me, and I will explain to you how to apply for that. With that, I would like to conclude, and thank you for your attention.